Hello, hello! This video is going to be all about projectile motion. It is not going to be much different from what you watched in class if you happen to be here for class. If not, here's just me working out this example again. So, projectile motion, what it means to be a projectile is any object that is launched. So that could be kicked, that could be thrown, that could be headbutted, that could be somebody runs off the edge of a cliff, somehow launching yourself into the air, and then after which you are only affected by gravity after you are launched. Okay, the only force affecting the object after it's been launched is gravity. All of these are true, or these two statements are true about projectile motion. So it must be launched and must only be affected by gravity after it's been launched. So few vocabulary words just to make yourself familiar with. Launched into the air is called a projectile. The path that it takes is called the trajectory. We predict the path. And now that you've seen my face, hi, I'm Miss Bailey. I'm going to scooch my face off the page so we can focus on the math. There is independence of motion in 2 dimensions for every projectile. That just basically means the horizontal motion is independent of the vertical motion. They do not affect each other. We must treat sideways motion differently from up and down motion. When I launch something at an angle, it's going to be moving in 2 directions at once. It's going to be moving sideways the same time it's moving up and down. But both of these types of motions, the sideways motion and the up and down motion, act differently, so we must treat them differently. Well, that's a big blank slide. Don't know why that's there. But these are the different equations we are going to use because we will be treating those motions differently. So the horizontal direction will not be accelerating. The acceleration is 0 because I stay at a constant velocity the entire time horizontally. I never stop moving sideways. I don't speed up. I don't slow down. I just move the same speed the whole time. You're going to notice this equation is the velocity equation. It's just rearranged to have delta x all by itself. And then for the vertical motion, all of these equations are these constant acceleration equations that we used last unit. Because I know in the vertical direction, my acceleration is being affected by the force of gravity. So my acceleration for all of my objects will always be negative 9.8 meters per second squared. Cool, cool, cool. Why do we separate motions into x and y? Strictly because of gravity. Gravity only affects objects when they are moving up and down. If they are moving side to side, it doesn't slow them down or speed them up. It really just pulls objects down. So it only affects the y direction. That's what gives the acceleration in the y direction, is gravity. Okay, great. So I'm giving you a lot of information. We will do a problem, I promise. Typically what a problem will look like in this class is you will have something launched at some angle. You will be given the angle, and you will be given the initial velocity. I can break that initial velocity that's at that angle into how fast it's moving sideways initially and how fast it's moving up initially. Now this picture right here is not a picture of the entire motion of an object. Once it's been hit, it goes up and comes back down, similar to this picture that's down here. So that is just all of those arrows, all of those vectors are happening at the same instant at the beginning of the motion. So those are just telling me things about the velocity at the beginning. So now, don't forget stuff you knew about parabolas. Maybe some of you noticed this, maybe you didn't. These are still parabolas. We are used to have straight up and down parabolas from free fall. And maybe you remember some little tricks that like the velocity on one side is the same as the velocity at the exact same point on the other side, except one's positive and one's negative because one side's going up, one side's going down. Gravity is affecting my motion the whole time. Velocity at the top is 0. All of these things are still true. The big difference here is all of this is happening in the y direction. while moving sideways. So at the exact same time that parabola is happening, it's also moving sideways at the same time that it's moving up and down. So this x direction is being combined with the y direction, and that's how we get this wide-looking parabola like we do. So other things to remember is that the highest point in the motion happens halfway. So I need to remember anytime I'm looking for max height, top of the throw, that occurs at half time, halfway through the motion. And a few new things. If a problem is asking you to solve for range, they are talking about delta x, which can be confusing because in math, range means something different. I like to think of range as like how far down range does something end up. When I think of the phrase down range, I think how far away from me is something. So range definitely means delta x. Height is delta y. Great, you can read the rest of the slide. I am going to go ahead and skip and do the practice problem that is on here. So a golf ball is hit with a club and has a trajectory at an angle of 53 degrees above the horizontal with an initial velocity of 10 meters per second. I'm going to start by drawing a picture of that. So golf ball is hit at an angle 53 degrees above a horizontal. So I'm going to draw a line 53 degrees above a horizontal line. And that ball is moving at that angle at the velocity of 10 meters per second. So I'm just going to label that right there on that arrow that's at that angle. Now this problem is asking me what are the x and y components of the velocity. They are basically just asking me to solve for how fast is it moving sideways and how fast is it moving up. Okay, keep in mind, y'all, that this is the actual initial velocity of the ball. But because this is happening in two different directions, in two dimensions, you could say, because it's moving up at the same time it's moving sideways, I can't plug that into any constant acceleration equation or constant velocity equation because part of it's doing each. So I have to separate it into those specific parts. So I'm going to label what I know. This side is also known as my hypotenuse. This would be opposite of the angle they gave me, and this would be adjacent. So I'm basically going to find the sides of this triangle to find these different velocities here. So I will use SOHCAHTOA. And if I'm looking for my y component, I know I'm looking for the opposite side, and I know the hypotenuse, so I'm going to choose the trig function with both opposite and hypotenuse in it. That is sine. So sine of theta equals opposite over hypotenuse. Sine of 53 would be my y velocity, my y component over 10. Multiply by 10 on both sides to get Vy by itself. So this is what I will type in the calculator. When you do so, you get that the y component is 8 meters per second, which maybe you also noticed this was a trig triangle. You could have maybe done this in your head without trig if you noticed that, but not necessary. So now to find my x component. I am looking for the adjacent side. I know my hypotenuse, so I'm going to use cosine of theta equals adjacent over hypotenuse. Cosine of my angle equals velocity x is that adjacent side over 10. I'm going to move 10 to the other side by multiplying. Now velocity x is all by itself. And I get my x velocity is equal to 6 meters per second. Excellent. Now there is a part 2 to this problem. How long does it take the ball to land is the first one. Well, now we are looking, how long does it take? At the entire motion of the object. I am not just looking at the beginning of the motion anymore. I am not just looking at my initial velocity anymore. what's actually happening, and I'll draw it in black maybe so it's easy to see over all these colors, is all of this is happening, all of these velocity vectors are happening at the very beginning of the motion, and the actual ball is kind of flying up in this big long arc shape. Delta y is occurring somewhere right there. Delta x is this big whole long distance all the way to the very end. You kind of get the idea. So since I'm looking for total time spent in the air, I can't just focus on these initial velocities that I found. I need to know stuff about the whole entire motion. So write down what we know and what we don't know. Well, write down what we know and what we're looking for. And keep in mind, you know a bunch of stuff about parabolas. There are things you can assume with parabolas, and I'll kind of walk you through that. So I'm going to zoom in to kind of make my little chart nice and big. I want to sort the two types of motions that are happening when I have something traveling at an angle. It's moving in the x direction and the y direction at the same time. And from earlier, we found that the x velocity, the horizontal velocity, is 6 meters per second. And we also found that the y velocity, and this is going to be an initial y velocity, is positive 8 meters per second. I say it's the initial and I also say positive because remember, the y direction, you are moving up and then moving down, but it's still that parabola shape. If I know my very, very beginning velocity at the exact same point on the other side, if I land at the same point, my velocity is the same, only negative. So my final y velocity will be negative 8 meters per second. I also know that gravity is affecting the motion of this object. So gravity accelerates all objects at a rate of negative 9.8 meters per second squared. The problem is asking me, how long does it take? So I am looking for time. Time is the one thing I won't plug into an x or y column because time is the one value that's going to be the same for both numbers. So, sorry, pause for a second. It takes the same amount of time to go up and all the way back down as it does to travel the entire x distance. So all of this is happening at the same time. Time is the one value that's going to be the same for both of them. So I don't like to write time in either column. You could write it in both. I just like to write it underneath to remind myself that it's the same for both. Something else I don't want to forget that I know some of you don't like to write this, that's okay, but I like to write as much information as I know. I know velocity at the top in the y direction is 0 because very briefly, when I am moving side to side like this, I am not completely at rest at the top because it's still moving sideways. But I know I stop moving up at the top and I start moving down. I change direction. Great, I know a bunch of information. Now I need to pick out an equation to use. And I can kind of rewrite these equations somewhere. I'll write them right here. So I'm going to make a different chart, x and y. For the x direction, I'm only ever going to use my constant velocity formula. For the y direction, I can use any of these three. I don't use one of my constant velocity formulas because it doesn't have acceleration in it. So out of those formulas, the one I would choose to use, me personally, would be number 2. Oh, just kidding. We're looking for time. I lied to you. The one I would use would be number 1. I know my initial and my final velocity. I also know my acceleration in the y direction. So I would absolutely use that top y formula to solve for time. Some of you might be like, why don't I use the x equation? It's because I don't know delta x. I need these other two values in order to solve for time, the missing one, and I don't have everything, so I'm not going to use that here. Final velocity equals initial velocity plus acceleration times time. I'm going to plug in stuff without units because I'm being lazy. -16 equals -9.8 times time, but then I'm going to divide. Time equals about 1.63 seconds. So now, how high does the ball go? I am now looking for delta y. And me personally, I would use this second equation to solve for it. You could use this last third equation if you wanted to, but I have a couple of issues with using that last third equation. First issue is that equation has time in it, and I calculated time. I like to avoid using calculated numbers where I can because there's a chance I could have calculated incorrectly. The other thing I don't like is, remember, when I am looking for height, max height, that happens in the middle of the motion at half time. So I need to remember to multiply time by 1/2 whenever I'm looking for height, peak of the throw, top of the motion, because that only takes half the time to get there. I bet money if you pick this equation with time in it, some of the time, no pun intended, you are going to forget to divide that time in half. So I like to be safe and just use this formula without time because that's too much to remember about time. And the thing about this is, if you're solving for peak or max height, you have to remember to use this velocity at the top somewhere. Plug in 0 for either one of your velocities, it doesn't matter which. I like to plug it in for my initial velocity just because when I rearrange, I don't have to rearrange as much. 0 squared just becomes 0, so that half of the equation is already tremendously shorter. -8 squared is just 64. 2 times -9.8 is -19.6. So now I just divide. And I get about 3.3. When you type this specific thing into your calculator, it's negative, but since they're asking about height, you can just drop the negative. Why that happens is if you're treating 0 as your initial, you're starting the measurement from the top of the motion, and the second half is what you're measuring, which is still correct. It'll still give you the same number, but it's telling you that you're moving down at that point, at that half. So now what is the ball's range? How far away does it land? We are now looking for delta x. What's nice about this is since I'm looking for delta x, I know I'm really only going to use that equation. So I'm going to go ahead and rearrange it to get delta x all by itself, so all I have to do is plug in stuff. Velocity x, we know, we solved for it. It's 6 meters per second. Time, I am going to use the whole time here because you're going to notice if I look at my picture, it's going to take the whole amount of time for me to get the whole x direction, the whole x distance that's traveled. I need the whole amount of time to do that. And I have to use my calculated number here. There's no way around that. But when I type this in my calculator, I get 9.78 meters, which seems like an okay number. One last thing I want to mention is a common mistake I see in these problems, which I actually guess I'm not going to tell you because I can't zoom up. My iPad froze on me again. But we didn't use this number. We solved for the sides of this triangle. And we got 8 over here and 6 over here. We never used 10 meters per second in an equation. Again, that is because those motions act differently, and we have to use specific equations for each part of that. 10 meters per second is staying at a constant velocity while speeding up and then slowing down, or slowing down then speeding up. Part of it's changing and part of it's staying the same, which is complicated to deal with. That is the whole reason we split it into this part of the motion is changing and this part isn't, so we can handle it a little bit easier. So never, ever, ever use that hypotenuse in an equation. It has to perfectly fit into the x horizontal or vertical category in order for me to use it in one of those equations. So just be very careful. I'm sorry my iPad froze again. It just keeps happening. But please come see your teacher for tutoring, ask questions, message us if you have any questions. Good luck.